The principle of operation for busbar protection primarily relies on the differential protection method. This method is designed to detect faults on busbars and associated equipment by measuring the currents flowing in and out of the busbar. The busbar protection system operates on Kirchhoff's first law, which states that the sum of currents entering a junction must equal the sum of currents leaving it. Therefore, under normal conditions, the total current flowing into the busbar should equal the total current flowing out. Any discrepancy indicates a fault. The busbar differential protection relays compare the currents entering and leaving the busbar. If there is a faulty G, a short circuit, the current entering the busbar will differ from the current leaving, resulting in a differential current that exceeds a predetermined threshold. This triggers the protection system to isolate the faulty section by tripping the relevant circuit breakers. There are primarily two types of differential protection relays used for busbar protection. First, low impedance differential protection. This is the most commonly used method. It is sensitive and can adapt to complex schemes, allowing for operation even during substation reconstruction. Secondly, high impedance differential protection. Some system operators still use this method. It is typically less sensitive than the low impedance method but has advantages in terms of simplicity and cost effectiveness. Busbar protection systems may also incorporate additional tripping criteria to enhance reliability and security, such as check zones, to prevent false trips due to malfunctioning disconnectors. Current direction supervision ensures that all currents in the bus are moving in the expected direction. Dynamic topology replication. A modern busbar protection system should dynamically replicate the bus topology and include design flexibility to accommodate various bus arrangements. Busbar protection operates by continuously monitoring the currents flowing through the busbar and using differential protection principles to detect faults, ensuring the fast and selective isolation of any faulty sections. Busbar differential protection configuration can be categorized into two main types, one centralized and second decentralized arrangements. Centralized arrangement. Numerical centralized busbar protection is typically found in new substations or in retrofitted old conventional busbar protection systems where the cabling is still in good condition. The amount of cabling in a centralized arrangement is approximately the same as in conventional arrangements. Advantages of a centralized arrangement include easy adoption of functionality and simple arrangements of inputs-outputs. It allows for fast and easy connection with substation automation systems, which facilitates quick fault analysis and monitoring. Decentralized arrangement. In the past, busbar protections were constructed centrally, requiring considerable interconnection between various protection panels, which made engineering, commissioning, and maintenance time consuming and costly. Nowadays, decentralized busbar protection is more common in new substations, especially at higher voltage levels 330 kV and above. This type reduces the amount of cabling and mitigates electromagnetic compatibility (EMC) issues due to the use of fiber optics. The choice between centralized and decentralized configurations often depends on local conditions and the specific requirements of the transmission system. Special busbar arrangements components and their protection. Here are the key points to remember. End fault protection. This functionality is crucial for protecting zones located between a circuit breaker and a current transformer when the CB is open. It aims to handle small zone faults that the busbar protection BBP cannot clear on its own. This protection sends a trip signal to the line distance protection at the remote end to eliminate the remaining fault. Dead zone blind spot. The section between the CT and CB is termed the dead zone. End fault protection is activated only when the CB is open. When the CB is closed, this function is not in play, allowing for a fast fault clarification. Faults in bus couplers. The presence of CTs on either side of bus sections and couplers is crucial for ensuring that faults can be detected and cleared. The strategy used can be selective or unselective, depending on the arrangement of the CTs. Protection during on-load busbar changeover. The busbar protection system must be capable of detecting faults occurring during an on-load busbar changeover, ensuring that the connected bays receive appropriate trip commands. Bus coupler time delay. A time delay is necessary for bus coupler operations, which should be shorter than the delay of Zone 2 distance protection, typically ranging from 0.15 to 0.3 seconds. Policy for isolator alarm. The switchgear positional information is crucial for determining the primary arrangement of each busbar section, and policies may vary on how to respond to isolator alarms. These strategies and components are essential to ensure that busbar protection systems can effectively manage various scenarios and maintain the stability and safety of the transmission system. Circuit breaker failure protection BFP is a local backup protection function that operates selectively in the event that a circuit breaker fails to interrupt fault current despite receiving a tripping impulse from its protection. The goal of BFP is to minimize the number of bays tripped, ensuring that only the necessary sections are affected. Several types of BFP schemes exist, and they typically rely on the occurrence of two signals within a specified time frame, an external start signal and confirmation of an overcurrent condition, or alternatively, a circuit breaker contact signal. The external start signal is usually triggered by a trip command from any protection function, such as a distance relay or a differential relay, depending on the type of feeder. The BFP operates based on the following principles: confirmation of overcurrent. The main criterion for the operation of the BFP is the detection of an overcurrent through the circuit breaker. This ensures that the circuit breaker has indeed failed to operate. Circuit breaker position criteria. The position of the circuit breaker open or closed is also monitored to confirm whether a fault condition exists. Retrip function. If the initial trip cannot clear the fault, the BFP can initiate a retrip of the circuit breaker after a short time delay, typically less than 100 milliseconds. If this retrip is also unsuccessful, a second stage of the BFP will trip all circuit breakers connected to the same busbar section. Contingency arrangements. BFP schemes can be combined with other protection functions, such as distance protection, to ensure that if BFP is unavailable, alternative measures can still provide protection. Busbar protection systems protect substation busbars and associated equipment from the consequences of short circuits and earth faults. In the long-ago early days of power system development, no separate protection device was used for busbar protection. Remote end-line protection served as the main protection for busbar faults. As a result of increased network short-circuit capacity, dedicated differential relays for busbar protections have been applied to minimize the tripping time of the protection and to limit the damage caused by high fault currents. Today, busbar protection systems are used. And even double busbar protections may be applied. The generic transmission system's key issues i.e. reliability, operability, maintainability and cost need to be addressed when designing a substation and selecting a busbar configuration and consequently a busbar protection scheme. At EHV-HV levels, solutions that provide a high degree of reliability can be justified. A busbar protection system should dynamically replicate the bus topology. It should also contain sufficient design flexibility to protect all existing bus arrangements. In general, the main requirements for busbar protection include: security probability of an unnecessary protection operation for through faults out of zone faults is low. Dependability probability that the protection will not operate for a fault on the bus in zone faults is low. High-speed operation is required to limit equipment damage and to preserve system transient stability. Sensitivity, the ability to detect and clear high-resistance faults. Selectivity, the ability to isolate only the faulty bus section. Purpose: busbar protection systems safeguard substation busbars and associated equipment from short circuits and earth faults. Historical context: initially, no separate protection devices were used for busbar protection. Remote end-line protection served as the main protection for busbar faults. Evolution: increased network short-circuit capacity led to the use of dedicated differential relays for busbar protection. These relays minimize tripping time and limit damage from high fault currents. Modern systems often use double busbar protections. Design considerations: key issues, reliability, operability, maintainability, and cost. High reliability solutions are justified at EHV-HV levels. Busbar protection systems should dynamically replicate bus topology and offer design flexibility to protect all bus arrangements. Main requirements: security, low probability of unnecessary protection operation for through faults out of zone faults. Dependability, low probability of failure to operate for a fault on the bus in zone faults. High-speed operation to limit equipment damage and preserve system transient stability. Sensitivity, ability to detect and clear high-resistance faults. Selectivity, ability to isolate only the faulty bus section. Bus differential protection: based on Kirchhoff's first law, the sum of currents entering and leaving a bus must be zero. Protects a bus with multiple feeders by ensuring the sum of incoming currents equals the sum of outgoing currents. Fault detection: an internal fault in zone fault is indicated if the current sum is not zero. External faults can cause high currents that may saturate CT's current transformers, leading to false differential currents. Challenges: CT saturation can cause incorrect relay operation by providing false current magnitudes. Manufacturers use algorithms to maintain relay stability and prevent unnecessary operations during CT saturation. Kirchhoff's current law: the vector sum of all currents at a node or bus is zero. Application in bus protection: current transformers monitor currents entering and leaving a bus. Bus differential protection compares incoming and outgoing currents. Any significant difference indicates a bus fault that needs quick isolation. Bus differential relays detect differential current and trip associated breakers to isolate faults. Do not require magnitude or phase angle compensation like transformer differential relays. Do not need to handle magnetizing inrush currents. Implementation: simple schemes can parallel CTs from all circuit breakers on the bus. All paralleled CTs must have the same ratio to ensure accurate current comparison. Relay setup: a simple bus differential scheme can use an instantaneous overcurrent element with a sensitive pickup, assuming no current flows to the relay under normal conditions. CT performance: all paralleled CTs must have the same ratio and perform identically, even under external faults with heavy currents and asymmetrical waveforms. CT saturation issue: conventional iron core CTs can saturate, causing their secondary output to inaccurately represent the primary current. Differential relay challenge: relays must distinguish between true internal bus faults and false differential currents caused by CT saturation during external faults. Numeric current differential, high impedance, stabilized, etc. The primary principle of busbar protection is the current differential principle due to its high sensitivity. Nowadays, numeric current differential relays are predominantly used because microprocessor technology enhances both performance and cost effectiveness. These relays are easily adjustable to accommodate changes in substation configurations or CT parameters. Modern technology allows for the protection of complex substations and ensures continuous protection even during reconstruction phases, which often require temporary operations. A key feature of numerical relays is their built-in monitoring system, which detects and alarms faults within the equipment. Main types of differential current protection relays: low-impedance differential protection and high-impedance differential protection. Currently, low-impedance differential relays are more commonly used, although high-impedance relays are still in use by some operators. Each type has its own advantages and disadvantages. Low-impedance relays offer the benefits mentioned earlier, while high-impedance relays are easier to extend, require less space, and are less expensive. However, low-impedance relay hardware can be shared with breaker failure protection, reducing costs. Users must evaluate and choose the best solution based on their specific application and installation needs. CTs can saturate during severe faults, causing small performance differences. Therefore, stabilization or additional tripping criteria are recommended, especially for low-impedance relays. The most common stabilization method for low-impedance relays compares the differential current vector sum of currents from all CT inputs with the arithmetic sum of these currents. The higher the arithmetic sum, the greater the differential current needed for relay operation. Supplemental protection functions: end-zone fault detection, breaker failure detection, open or shorted CT detection. If a fault occurs between a circuit breaker and its associated CT, the fault cannot be interrupted by opening all breakers in the substation. End-zone protection logic detects when the breaker is open but the current through the CT has not dropped to zero, sending a transfer trip to the remote breaker to interrupt the fault current. Alternatively, a teleprotection signal can be sent to distance relays at the remote end to accelerate their operation. In a low-impedance scheme, an open or shorted CT produces a differential current proportional to the load current on the faulty circuit. Settings can eliminate differential current under normal load conditions, allowing a sensitive threshold to detect an open or shorted CT. This threshold can trigger an alarm, disable the busbar protection, or trip the bus. A more sophisticated method detects changes in differential and restraint currents, where the loss of CT output increases differential current and decreases restraint current. Arc protection light sensitive. Arc fault protection is used for the rapid clearance of arcing faults in busbars, circuit breaker compartments, and associated cable boxes in air-insulated metal-clad medium and low-voltage switchgear. Arc flash detection methods. Arcing faults release large amounts of radiant energy, including light and thermal energy. The light intensity from an arc can be thousands of times higher than normal ambient light. Arc flash detection relays utilize this phenomenon to achieve faster response times, providing greater protection than conventional relays. Conventional current-based protection techniques can be slow in clearing arcing faults, increasing risks to personnel and equipment damage. Optical detection techniques in arc fault protection enable fast clearance of arcing faults. AFP can detect arc flash events and send a trip signal within 2 to 4 milliseconds using high-speed output contacts, or 15 milliseconds for relay contacts. While light detection is the fastest method, many systems use a combination of parameters: light, current, sound for detection. The most efficient and cost-effective method combines light and current detection. Arc flash detection system components: arc monitor unit, control unit, optical detector, current transformer. The control unit receives signals from a high-sensitivity light detector and an upstream current transformer to determine if the circuit breaker should be triggered. This process must be fast and reliable to minimize danger and damage. Fiber optics, with their speed and EMI immunity, are ideal for arc flash detection systems. Optical detector unit includes an optical emitter and receiver, an optical sensor bare fiber loop, and fiber optic cable. The optical sensor collects flashlight and transfers it via fiber optic cable to the receiver, which converts the optical signal to an electrical signal for the control system. Types of optical sensors. Point sensor uses a light sensor and optical receiver to detect light in a specific area. Loop sensor uses a loop of bare fiber strategically positioned throughout the equipment. Arc flash detection system components: arc monitor unit, control unit, optical detector, current transformer. The control unit receives signals from a high-sensitivity light detector and an upstream current transformer to determine if the circuit breaker should be triggered. This process must be fast and reliable to minimize danger and damage. Fiber optics, with their speed and EMI immunity, are ideal for arc flash detection systems. Optical detector unit includes an optical emitter and receiver, an optical sensor bare fiber loop, and fiber optic cable. The optical sensor collects flashlight and transfers it via fiber optic cable to the receiver, which converts the optical signal to an electrical signal for the control system. Types of optical sensors. Point sensor uses a light sensor and optical receiver to detect light in a specific area. Loop sensor uses a loop of bare fiber strategically positioned throughout the equipment. Busbar protection blocking scheme. Supervision or blocking criteria. The absence of differential busbar protection in a substation can significantly impact the stability of nearby power plant units. Ensuring operational reliability during a short circuit is crucial, as losing an entire substation due to busbar protection failure is unacceptable. Therefore, real-time monitoring of busbar protection functionality is essential. This includes verifying the accuracy of input data acquisition and the functionality of internal protection components. The primary busbar protection fault supervision functions include detecting faulty current measurements, disconnector position errors, and internal component failures. These supervision functions continuously operate to prevent false tripping and ensure reliable busbar protection. Current measurement supervision. This function monitors the differential currents, zone differential currents, and check zone differential currents in real time. If a faulty current is detected, the following actions can be taken: alarm possibly delayed, full busbar protection blocking either completely or only for the affected phase, partial zone busbar protection blocking only for the affected zone and phase, disconnector position supervision. This function monitors the real-time status of disconnector positions, detecting any incorrect or faulty positions. Internal component failure supervision. This function oversees various internal components, including watchdogs, bay links for decentralized arrangements, and power supplies. When a faulty disconnector position or internal component failure is detected, the actions can include alarms possibly delayed or full partial busbar protection blocking. Busbar splitting. Busbar differential protection is defined by its protection zones, which isolate bus segments using circuit breakers in the event of faults. The goal is to isolate only the affected busbar section after a fault. When multiple protection zones are applied, a busbar splitting strategy is implemented. The positions of the current transformer CTs are crucial for optimizing this strategy. In the event of a busbar fault, the protection system trips the circuit breakers for the specific busbar section involved. The CBs and disconnector positions are essential for accurate differential current computation and effective busbar splitting during faults. Utilizing multiple measuring zones enhances selectivity. Various busbar switching schemes exist, each with multiple variants. Double busbar with transfer bus. To ensure selective busbar protection, position inputs on each disconnector and circuit breaker are required. These inputs help select the correct differential current measurements for different zones and achieve proper busbar splitting during faults. Mesh busbar scheme. This scheme features a fully selective protection system with busbar differential protection at each corner. A fault at any corner trips the two associated breakers and initiates inter-tripping to open circuit breakers at opposite ends. Each busbar is considered individually, and a single busbar scheme is applied to each. More complex schemes can protect the entire substation selectively, requiring additional CTs and bay units of busbar protection in every branch. Direct trips to remote substations are also necessary. Faults in branches can be selectively detected and isolated. Distance protection relays are primarily used as a backup for busbar protection or during the maintenance of busbar differential protection. There are several ways to utilize distance protection. Zone 2, employing Zone 2 of distance protection from the opposite end of overhead lines or underground cables. Reverse zone, using a reverse zone oriented towards the busbar for transformer or overhead line distance protection. Coupling circuit breaker, utilizing distance protection to trip the coupling circuit breaker, with a blocking scheme between distance protections in a ring substation topology. During the maintenance of busbar differential protection, it may be necessary to adjust distance protection settings X reaches, R reaches, or grading times. These adjustments are sometimes required to ensure the stability of the generator in the area or to maintain the integrity of the GIS busbar in case of a fault during busbar differential protection maintenance. Additional tripping criteria for BBP differential: check zone to prevent maloperation due to disconnector auxiliary contact failures. Substation configurations may require an additional trip criterion, such as check zones. The check zones measuring system detects short circuits across the entire busbar, disregarding disconnector positions. Disconnector positions are only considered in special cases, such as for transfer or combined busbars. The entire substation is treated as a single node, summing the currents entering the node according to Kirchhoff's current law. A fault is indicated if the check zone currents do not sum to zero, regardless of the disconnect switch's status. If the normal differential operating current is non-zero and the check zone operating current is zero, a faulty disconnect status contact is likely the cause. Check zone supervision of the normal differential element significantly reduces the risk of a false trip. Current direction: there are additional options for a second trip criterion to supervise the differential element. An advanced differential relay can use a directional element to provide extra security during an external fault with CT saturation. During such events, fault current contributions flow through each non-faulted terminal and aggregate in the faulted terminal, causing the CT on the faulted terminal to saturate and produce a false operating current. However, the current in the faulted terminal will be out of phase with the other zone currents, indicating an external fault. The directional element selects one of the currents as a reference and calculates the phase angles of the other currents relative to this reference. The element declares an internal fault only if all currents are substantially in phase, thereby supervising the normal differential element. Phase under voltage release criterion: the busbar protection tripping command is released by under voltage function. The under voltage function senses voltage collapse during short circuit on a busbar. In case of current transformer circuit failure in a bay, the missing current will cause differential current in the measuring element and it can cause unwanted trip of this busbar section. In order to avoid this faulty trip, the measuring element can trip the busbar section if the under voltage release criterion is fulfilled. Busbar differential protection configuration: centralized arrangement. Numerical centralized busbar protection is common in new substations and in retrofitted older substations where the existing cables are still in good condition. In this setup, the amount of cabling is similar to that in conventional arrangements. Cabling reduction is possible only if additional protection functions, such as busbar and circuit breaker failure protection, are integrated into the busbar protection relay. The benefits of numerical protection equipment include easy functionality adaptation and simple I/O arrangements. Additionally, numerical techniques facilitate quick and easy connections with substation automation systems, enabling rapid fault analysis and monitoring. Decentralized arrangement: historically, before the advent of numerical decentralized busbar protections were centrally constructed. All process data, including CT currents, isolator positions, and tripping channels, had to be wired back to the central busbar protection panel. Significant interconnections, such as those for starting circuit breaker failure protection and blocking auto reclosure, were required between protection panels. These conventional arrangements involved extensive cabling, making engineering, commissioning, and maintenance time consuming and costly. Special busbar arrangements: components and their protection, and fault protection. Dead zone blind spot. A fault between a circuit breaker and a current transformer, and fault protection addresses faults in the bay between a circuit breaker and a current transformer known as small zone faults. This protection is implemented for all bays except bus sections, couplers, and shunt equipment, covering the zone between the CT and the CB when the CB is open. While busbar protection detects these faults, tripping the CB alone does not clear them. This is managed by applying CB fail or an interlocked overcurrent relay, depending on the voltage. Circuits with end fault protection prevent busbar zone tripping for small zone faults and only intertrip the respective remote and feed end to clear the fault. Shunt equipment, such as shunt reactors, MSCDNs, SVCs, HVDC converter transformers, and HVDC harmonic filters, generally do not require end fault protection. The measuring range of busbar protection BBP is limited by the CT location, with the section between the CT and CB referred to as the dead zone blind spot. Using end fault protection in the bus coupler enhances protection performance when the CB is open, extending the protection range to include the dead zone. End fault protection is active only when the CB is open. Fault in a bus coupler or a switched busbar in low-impedance busbar protection schemes, or bus sections and couplers with CTs on either side create overlapping zones. It is crucial to account for small zone faults with various disconnector combinations in open and or closed states. The scheme must ensure proper discrimination to avoid nuisance or unwanted tripping following a busbar fault. When a fault occurs in the overlap between two zones, such as at a bus section or bus coupler with the circuit breaker closed, both zones should trip simultaneously. This will immediately clear the fault, though not selectively. There are two other methods to protect these bays: selective protection with delay. This method prioritizes selectivity over speed. If a fault occurs between CTs, only the CB in the bus coupler or bus section trips. Subsequently, these two CTs belong to different zones of the BBP, allowing only the faulted bus to be switched off. A small delay of about 100 milliseconds is necessary to let the CB in the bus coupler or bus section open and for the BBP to reconfigure the substation. The CB state must be signaled to the BBP. Unselective and delayed protection. This method is simpler and more cost-effective but is both unselective and delayed. It can be used if stability and power outage are not major concerns. Circuit breaker failure protection operating principles. The circuit breaker failure protection (CBF) function acts as a local backup protection, operating selectively when a circuit breaker fails to interrupt fault current in one or more bays despite receiving a tripping impulse from its protection system. Selectivity here means tripping the minimum number of bays necessary, typically those from a specific busbar section or system. Several types of CBF protection schemes are detailed in IEEE STDC 37-119-2016. The simplest scheme relies on two signals within a specified time frame, an external start and an overcurrent condition, or CB contact information, or both. The external start is usually triggered by a trip command to the circuit breaker from any protection function. For instance, in a line feeder, this could be a trip from a distance relay; in a power transformer feeder, it could be a trip command from a differential relay; and for any feeder connected to a special busbar, it could be from a BBP relay. Circuit breaker failure protection operating principles. The overcurrent relay confirmation is essential for verifying that a circuit breaker has interrupted the current and provides security against unwanted start signals, especially during testing. For feeders with weakened feed, the circuit breaker auxiliary open contact 52A is often used instead of current-based confirmation. The time delay is set according to network stability requirements and is crucial for coordinating with remote backup protections. The scheme's output can result in different actions: our trip function, a backup trip function, and inter-tripping. It uses input CT, wiring, relay input circuitry, and firmware to issue the trip command and determine if the breaker has failed. Multiple operational copies of the BF function can potentially compromise its security. Some multi-input relays mitigate this by allowing different CT, wiring, and relay inputs for the BF function. The retrip function typically involves two independent tripping circuits. Protection devices in the bay trip on the first circuit, and after a short delay less than 100 milliseconds, the BFP sends a repeated trip signal to the circuit breaker on both coils. If the retrip is unsuccessful, the second stage of the BFP, with a time delay of around 250 milliseconds, opens the circuit breakers connected to the same busbar section. Contingency arrangement in case of BBP failure. Historically, busbar protection systems used a 2 out of 2 scheme, requiring both check and discriminating zones to operate for tripping. With the advent of numerical busbar protections, this requirement has been relaxed, allowing single units to be installed on a single CT per circuit. However, if a distributed unit or the central unit fails, the entire busbar protection for one or more sections is lost, potentially taking many circuits out of service until repairs are made. Two contingency options allow busbar sections to remain in service. Second central unit. Install a second central unit with associated fiber optic connections. If the first unit fails, the busbar protection can be manually switched to the second unit to maintain service. Adjust protection on feeders. Modify the protection arrangement on in-feeding circuits to provide limited busbar protection. This can be done using feeder distance protection with fast discriminative reverse zone 3. When activated, this zone should trip not only the local circuit breakers of the feeders but also other connected base circuit breakers E.G, transformers, shunt plants via a separate cross-tripping scheme. The time setting for reverse zone 3 must be properly graded with all feeder distance protections to ensure quick busbar fault clearance without tripping for faults within zone 1 of the feeder protections. Direct and selective tripping. Direct tripping. This involves the immediate tripping of the remote end of a feeder connected to a double busbar substation when busbar protection operates. It is achieved through direct transfer trip DTT and/or unstabilization of circuit protection by busbar protection trip relays or back trip receive trip relays with selectable links inserted. Interlocked current trip relay links should also be inserted. Note that unstabilization may not be used in modern systems but exists in some legacy installations. Selective tripping. This involves tripping the remote end of a feeder after a time delay, initiated by the ICTR, determined by the circuit breaker fail timer. It is achieved through inter-tripping and/or protection unstabilization. For selective tripping, links associated with BBTR and BTRTR must be removed, and ICTR links inserted. ICTR may also operate for end fault protection to inter-trip the remote end circuit breakers. Requirements for direct tripping: remote end of a 2-ended feeder connected to a double busbar substation. Remote end of a 3-ended feeder connected to a double busbar substation where fault clearance and CB fail time is unacceptable. Local substation indoors with CTs on the line side only. Outgoing feeder is a transformer feeder with LV side circuit breaker at the remote end. Local SGT LV circuit breaker connected to LV side KV at the local end. Situations where CB fail protection delay affects generator stability or continued energization from the remote end is unacceptable. No requirement for direct tripping from bus sections or couplers. Requirements for selective tripping: feeder is a teed feeder, including those with remote termination at a double busbar or mesh corner connected to an interconnecting transformer. Feeder's remote termination is a mesh corner, with or without a connection to a supply transformer. If delayed tripping causes instability, direct tripping should be adopted.